Okay, so let's think about what we talked about in the last lecture. Just think about the computational structure that was introduced, where we mapped an image, an intensity image, to a gradient field of that image. So the gradient field at every point in space has two components. So you've got one component representing the rate of change of intensity as you move in a rho direction, the other component giving you information about rate of change of intensity as you move in the other direction. So rho direction, column direction. So the two components at each point in space come from two pixels that are at the same locations in two images. Okay, so if you take one pixel in your input image, you map that to two pixels at the same locations, at the corresponding locations in your row and column gradient images. To produce those two images from your single input image, what you did is you convolve with one mask to give you the row gradient component, and convolve with the same image, the input image, with a second mask to give you the column component of gradient. So this idea is the start of, it's a very simple example of what's called a filter bank. So the filter bank is a concept where you have an image, a signal, whatever it may be, and instead of passing it through one filter, you pass it through multiple filters, and you use the results in parallel rather than putting things sort of sequentially. But that parallelism is very important. It's a very, very important concept. And it doesn't mean you necessarily have to actually do the computations in a strictly parallel fashion, but the way that the general, let's say, conceptual structure is like this. So you've got your image here, that's the input image, and in general, rather than just having two separate convolution masks, one for, let's say, HM and the other for HN, you now have capital C number of convolution masks, where C is chosen as a notation to align with the idea of channels in convolutional neural networks or in deep learning. So this idea of having multiple convolutions in parallel, all of these operations are linear, so they're linear neighborhood operations, but each convolution mask provides a different piece of information. So the key thing to recognize is that if you apply large C number of convolution masks, then you get large C number of resultant images that then represent an output space from this structure that's known as a filter bank. In this case, everything up to this point, well, let's say the outputs here are obtained from a linear filter bank. Excuse me. Now, we can then take that a bit further by combining these outputs in some way to give us what's called a feature map. And so that's the next thing we're going to look at, which is the idea of a feature map. So let's just jump back to that. And so here is an example of what's called a Lowe's texture map. And it's done by taking the leaf on grass image and applying 9 different convolution operators to that leaf on grass image. So what are those convolution operators doing? So they are designed, and these masks were designed back in the 1970s or 1980s by researchers who were trying to get a set of, or produce this kind of map excuse me, where large values in the map corresponded to the same spatial location or corresponding spatial location in the input image, and the values in the map measured some textural property of the same or the corresponding neighborhood in the input image. The way that this map is produced is by combining convolution operators that extract or respond strongly to very rapid changes in intensity over a small spatial scales. So many of these are directional. Of the 9 convolution masks, they're directional. And to make an output that is independent of direction of, say, structural or image structure, you combine the outputs from masks that are oriented in different ways. Much as we talked about the way that you take your two gradient field components and map that to a gradient magnitude, which doesn't depend on the direction in which the gradient is running. You can do the same thing with the Lowe's texture measures to measure this fineness of texture and combine the outputs from several masks, some measuring first derivatives, some measuring second derivatives, and I forget the details, but some might even be capturing sort of third derivatives, and all of these are in different directions. So by combining the outputs, you can get something that is a single map out of these 9 maps emerging out of the convolution. So just to be clear about the structure of that, we can now go back to our this image here. So the way that this works is that the after you get your results of linear convolution, you then take those outputs and map them through nonlinearities. Now the nonlinearities vary. They can be squaring functions, they can be squaring and square root, they can be absolute values, and they can be combined in different ways. So for example, if I have 2 second derivative, or let's say 4 second derivative operators, sort of looking in different directions, I can take the outputs of all of that subset of masks and apply a nonlinearity to the results, because the results are often positive and negative. So apply some nonlinearity to get rid of that, and then combine the values together by a summation operation as shown here. So this is not a precise representation of how those Lowe's texture energies were generated, but it's kind of an approximate representation of the general scheme of things. So this then suggests that rather than simply having a linear convolution operator, you have linear operator followed by some kind of nonlinearity. And so the linear operators themselves are very powerful, but you combine them with these nonlinearities and you can get things that you get that extra degree of flexibility that also in this case leads to this idea of invariance to spatial orientation of textures in order to give this fineness of texture measure. Now, let's come back very quickly to this image. So the thing about this image is that regions of the background grass regions are producing high values in this feature map compared to regions that correspond that are inside the leaf. So what these texture measures are picking up on, what they're giving us as the way they're responding, is that if the region of the local neighborhood has lots of fine texture in it, this combination of masks is outputting a large value, and that's why these areas are bright. The region of the leaf, if you look carefully at the original image, is relatively smooth, and so this feature map is producing relatively low values in regions that correspond to the interior of the leaf. So this is an example of what we call a feature map, and a feature map is, again, as you will see, it's the output of this thing over here. So the output of all of this is a feature map, which is generally the same size of the image. So I haven't drawn it here, but it's just like another image like that. So that's your feature map, and at the feature map you have some sort of property in that feature map that refers to a local neighborhood of the corresponding region in the input image. So we're going to come back to feature maps in chapter 5, and we're going to use this example, and we're also going to use another image that we've got further back in this set of slides, which is, if I remember correctly, it's this image. Wait a second. I think it's this image back here. So it's the image that measures the local average intensity by applying a 3x3 convolution mask. So we're going to use this image, which is the output of convolution, no nonlinearity, just this image itself, as another feature map. So in chapter 5, we're going to use 2 feature maps, and we're going to use that as the basis to explain how you can do unsupervised image segmentation, to explain the nature of classification boundaries, and just generally to explain the process of classifying from a feature space. So we're going to stick with a small feature space of just 2 dimensions, which we'll explain later on. But so this image we're going to come back to, and as I say, we're going to use this guy over here, the Lowe's texture features. So when we come to that portion of the the lecture in chapter 5, I will refer you back to this law's energy image. And so you can come back to this lecture, come back to that, how this is produced, so you get a better view of this. Okay, so the next thing I'd like to talk about is the scaling of convolution. That is, how the computational expense of convolution scales with the size of the image and the size of the mask.